So, hey everyone. Today we're happy to have Colin Defant from Princeton University, who's going to talk about stack sorting for Coxeter groups. Before we start, I just want to go over the guiding principles of GOCC. We're all learning, everyone has something to contribute, and no one has all the answers. So keep this in mind, and yeah, Colin, can't wait to hear about this stuff.
All right. Thanks. And yeah, thank you for everyone for coming, and also to the organizers for putting this seminar together. So my first slide is going to be me sort of just proselytizing about this type of combinatorics that I think is underexplored and deserves more attention. And then I'll focus on more specific things that I've been thinking about recently. So when I think of dynamical combinatorics, what I have in mind is there's some set X of combinatorial objects, and we have some function f from X to itself, and it's defined in some kind of combinatorial manner. And our goal is to understand the dynamics of this map F. And when I say understand the dynamics, what I really mean is we can draw this diagram of F. So this is some directed graph where the vertices are the elements of X. And for every vertex, you just draw an arrow from that vertex to its image under this map F. So this is what I'll call the diagram of the map F. And each connected component of this diagram is going to have some periodic cycle. But then we might also have these trees that are mapping into the points in the periodic cycles. Now, typically in the area that's now called dynamical algebraic combinatorics, people often focus exclusively on these periodic cycles. This is often because the maps that they're studying are just naturally bijective, and so they only have periodic cycles. That's all there is to study. But then there are some other times when maybe they have a map that's naturally not invertible, but they say, well, we only care about the periodic cycles. So let's just chop away these trees here. Let's just ignore the trees by chopping them away, and we'll just focus here on the periodic cycles. But I'm here to speak for the trees, for the trees have no tongues. And I think they have a lot of interesting things to say, so they should not be chopped away. So I want to focus on these non-invertible parts of these maps, namely the trees. This is sort of what I'm dubbing non-invertible combinatorial dynamics. And actually, for the maps that I'm going to be studying in this talk, their diagrams will just look like this over here, where there's one fixed point and everything eventually maps to that fixed point. So the whole diagram is going to look like one big tree. And before I go any further, I'll just make this definition. The forward orbit of an element of our set X under the map F, so this is O sub f of X. This is just this set X, f of X, f squared of X, dot, 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 where f to the I is the ith iterate of F. And even though I have the dot, dot, dots here, this is often going to be a finite set because the f to the I of X's are going to start repeating themselves if we get into a periodic cycle. Okay, so let me tell you about my favorite non-invertible combinatorial dynamical system, which is the stack sorting map. This was introduced by Julian West in his PhD thesis in 1990 at MIT. And he was defining this as a deterministic version of a stack sorting machine that was introduced by Donald Knuth back in the book, The Art of Computer Programming in the 1960s. So this function is something that I'll denote by S. So S here is the stack sorting map. And it sends permutations to permutations. I'm going to show you how it works with an example. I think the example will make the general case clear. So I'll show you how to find S of 416352. We're going to start by putting 416352 up on the right-hand side of this thing, which is called the stack. And at any point in time, the leftmost entry up here wants to go into the stack. But the rule of the stack is you're not allowed to have something big sitting on top of something small. So you cannot have a number sitting on top of something smaller than it. So in this example, the 4 wants to go into the stack, and that's fine because the stack is empty. And now the 1 wants to go in, which is also fine because 1 can just sit on top of 4. Now, the 6 wants to go in, but 6 cannot sit on top of 1 because 6 is bigger than 1. So before 6 can go in, 1 has to pop out of the stack. For the same reason, 6 cannot go on top of 4, so 4 has to come out. But now the 6 can go into the empty stack, and then 3 can go in on top of it. Now 5 cannot sit on top of 3, so 3 has to come out. But 5 can go on top of 6, and then 2 can sit on top of 5. And now that we have nothing left to push into the stack, we just empty the stack from top to bottom. So the 2 comes out, the 5 comes out, the 6 comes out, and we get the output permutation 1, 4, 3, 2, 5, 6. Now, it's not hard to show that if you iterate this map over and over again, you'll eventually get to the identity permutation, just the increasing permutation 1, 2, 3, 4, dot, 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 n. And it's also not very hard to show that the maximum size of a forward orbit of a permutation of size n, so here Sn is the set of permutations of size n, the maximum possible size of a forward orbit of a permutation of size n under this stack sorting map is exactly n. Again, this is not very hard to show. Now, here's a variant of the stack sorting map. This is called the pop stack sorting map, and I'll denote it by pop. This has a very similar rule. The only difference here is that whenever you pop a number out of the stack, everything has to pop out. So whenever one number comes out, everything comes out. So again, 4 will go into the stack just as before, and then 1 can go on top of it. And now 6 can't go on 1, so 1 has to pop out. But when 1 pops out, everything pops out. So the 1 and 4 come out together. Now, so far, this isn't any different from what we did in the previous case. So let me go a little further. 6 will go in, and then 3 goes in on top of it. Now, 5 can't go on 3, so 3 has to come out. But this time, when 3 comes out, everything comes out. So 3 and 6 both come out together. Then the 5 goes in, the 2 goes in, and then the 2 comes out, which means everything comes out. So they both come out together. And we get this output permutation 1, 4, 3, 6, 2, 5. Now, this map was actually originally studied in a paper by Peter Unger in 1982, and he was not coming from this combinatorial dynamics point of view. He was actually coming from the point of view of discrete geometry. He had a question involving the directions determined by a collection of points lying in the plane, and he managed to reduce this question to something about what we would now call the pop stack sorting map. So really, his discrete geometry question ended up reducing to something about this map. And in the process of proving the things he wanted to prove, he showed that the maximum size of a forward orbit under this pop stack sorting map is n, when you look at permutations of size n. And this is actually not so easy to prove. This actually requires quite a bit of insight on Unger's part. So it's really a non-trivial theorem to show that this is true. But again, it's not hard to show that every permutation eventually gets mapped to the identity. What is hard is showing that it requires at most n-1 iterations, basically. Okay, now the two definitions I've given here for the stack sorting map and the pop stack sorting map are sort of the standard definitions. There are what I would consider much more natural definitions for defining them. So if you think the definitions I've given are a little weird, I kind of agree. There are other ways of defining them that I personally think are more natural, but these are sort of the standard definitions, which is why I gave these. Okay, so here's a picture of the diagram of the stack sorting map on permutations of size 6. So there are 720 vertices here, and you can see they all get mapped into this big blob here. The identity is somewhere in that blob, and so they all map to the identity. And then this is a picture of the diagram of the pop stack sorting map on permutations of size 6. Again, everything eventually maps to the identity, which is somewhere in this blob here. And I have this quote from the Lorax by Dr. Seuss, and the Onceler said, "All my life I've been searching for trees such as these." So I thought that was kind of appropriate here. Okay, so last fall, I attended a GOCC talk, which was by Daniel Tamayo Jimenez. And he was talking about permutary sorting. And briefly in his talk, he mentioned the stack sorting map. And at the end of his talk, I asked him, do you think there's a way of generalizing the stack sorting map to Coxeter groups? And he said he didn't really have any ideas. And I said, yeah, I don't really know either. And then Galen said, well, maybe Colin will come back a week from now and he'll know how to do this. And I said, okay, sure, I'll come back a week from now and I will know how to do this. So it has been much more than a week, but now I've come back to the GOCC. And I think I have what I would consider a pretty reasonable definition of stack sorting for Coxeter groups. Before I tell you what it is, I want to give a brief crash course on Coxeter groups just so we're all on the same page. So I'm going to let S be a finite set. This is the set of what are called the simple generators of the Coxeter group. W is going to be the Coxeter group. It has this presentation here saying that it's generated by the simple generators. And if you take two simple generators, S and S prime, and you multiply them together and raise them to some exponent, you get the identity element of the group, which I'm denoting by E. And these exponents have to satisfy, first of all, that M of S comma S is always 1. This is just the same as saying that each one of your simple generators is an involution in the group. And then also M of S comma S prime is always equal to M of S prime comma S. And this is some integer that's at least 2 or infinity when S is not equal to S prime. And if it's infinity, then this relation is basically not there. So W is the Coxeter group. And I'm just going to assume that the Coxeter groups here are irreducible. I don't really lose anything by making this assumption, because if you understand the irreducible case, you can understand the reducible case. But I think for the presentation, it's just easier for me to assume everything is irreducible. So the prototypical example of a Coxeter group is the symmetric group Sn. It has simple generators S1 through Sn minus 1, where Si is this simple transposition that swaps I and I plus 1. Now, if you have an element little w in your Coxeter group, you can write it as a word in the simple generators. This is just because the simple generators generate the group. And so then if you take such a word, which is minimal in length among all words representing little w, then it's called a reduced word for little w. A standard Coxeter element of W is just an element that you get by multiplying all of the simple generators together in some order. So just write them down in some order and multiply them together. What you're left with is a standard Coxeter element. And the Coxeter number of the group, which I'll denote by H, is the order of this Coxeter element. So my convention is that if we have an infinite group, then the Coxeter number is just infinity. But if we have a finite irreducible Coxeter group, then actually this will be some number which is intrinsic to the group, in the sense that it doesn't depend on the choice of the Coxeter element, because all Coxeter elements of a finite Coxeter group are conjugate to each other, so they all have the same order. Okay, so think of this as just some special number associated to the Coxeter group. Okay, there are some natural partial orders on Coxeter groups, and I'm going to discuss the left and right weak orders. So the left weak order is defined by saying that an element V is less than or equal to an element W in the left weak order if there is some reduced word for W that has a reduced word for V as a suffix. And by suffix, I mean like a final segment of the word. Then the right weak order is defined in pretty much the same way. We just replace the word suffix by the word prefix. So V is less than or equal to W in the right weak order if there is a reduced word for W that has a reduced word for V as a prefix. And these two partial orders are isomorphic to each other as posets, because there's this simple isomorphism between them that just sends each element to its inverse in the group. This is a picture of the left weak order on S4. And then also a right descent of little w is just a simple generator that is less than or equal to little w in the left weak order. It might seem a little weird that I'm defining a right descent using the left weak order, but this is basically because an alternative way of saying this is that S is a right descent of W. If when you multiply W on the right by S, the Coxeter length goes down. But anyway, this is one way of thinking about it. Okay. So now if I have a poset, I'll call it a meet semi-lattice. If for any two elements of the poset, they have a unique greatest lower bound, which is called their meet, and it's denoted by this wedge symbol here. So this is X meet Y. And then a lattice is a meet semi-lattice that such that also whenever you have any two elements, they have a unique least upper bound, which is called their join and denoted by this V symbol here. So this is X join Y. So a lattice is just a poset in which any two elements have a meet and a join. A very important fact about Coxeter groups is that if you take the left weak order on a Coxeter group, then it is a meet semi-lattice. And also if the group is finite, then it's actually a lattice. Alternatively, I could have said right weak order here because again, the two partial orders are isomorphic to each other as posets. Okay. I'm almost done with the definitions here. I realize it's sort of a lot. So a semi-lattice congruence on a meet semi-lattice is just an equivalence relation that is compatible with the meet operation. In symbols, what this is saying is that if x1 is equivalent to x2 and y1 is equivalent to y2, then the meet of x1 and y1 has to be equivalent to the meet of x2 and y2. But in your head, you should just think this is some equivalence relation that is compatible with the meet operation. Okay. And then a lattice congruence on a lattice would be well, it's a semi-lattice congruence, meaning it satisfies this condition, but it also has to respect the join operation, meaning it satisfies a similar condition with the meets replaced by joins. So a lattice congruence is an equivalence relation that is compatible with the meet and the join operations. And this is a picture of a lattice congruence on the left weak order of S4. These colored things are the different equivalence classes. And this is just a technical definition that I'm going to need later. It's not like too important, but I'll just need it a little bit later. So a semi-lattice congruence, or if you like a lattice congruence, on the left weak order of a Coxeter group is essential if the identity element is in its own singleton congruence class. So here you can see the identity element 1, 2, 3, 4 is in its own singleton congruence class. So this is actually an essential lattice congruence on the left weak order of S4. Okay. Okay. So I want to give a couple examples of these congruences. The first will be the descent congruence, which is defined on the left weak order of an arbitrary Coxeter group. I'll denote it by this equiv sub des symbol here. So two elements of W will be equivalent in the descent congruence if they have the same set of right descents. Remember, a right descent is just a simple generator that is less than or equal to the element in the left weak order. So if two elements have the same set of of right descents, then they are equivalent in the descent congruence. And this is a picture of the descent congruence on the left weak order of S4. So there are these different colored regions representing the equivalence classes. Okay, now on symmetric groups, there's this nice congruence called the Sylvester congruence, and it's defined using decreasing binary plane trees. So a decreasing binary plane tree is a rooted tree in which every vertex has at most 2 children. Every child is designated as either a left child or a right child, and it's bijectively labeled with the numbers from 1 to n, so that if you start at any vertex and you move down a path, the labels decrease as you go down that path. For example, if I started at the root and walked down this path here, I'd read off 6, 5, 3, and so they're decreasing as I go down. And there's this nice bijection between decreasing binary plane trees and permutations, which is called the in-order bijection. Basically, in order to read a tree in order, you just sort of read the vertices in order from left to right. So here I would read 4, then 1, then 6, then 3, then 5, then 2. So I get the permutation 4, 1, 6, 3, 5, 2. There is a way of making this rigorous, and it is actually a bijection. But the point is just there's some bijection between decreasing binary plane trees and permutations.
And just to check, so if year 1 was like on the other side of 4, would that be considered a different binary plane?
Yes, yes, definitely. If I swung that right edge over to make it a left edge, that would be different.
Okay.
And it would correspond to a different permutation. Yeah, thank you. Okay, so the Sylvester congruence on the left weak order of Sn, this is actually a lattice congruence. It's actually an essential lattice congruence on the left weak order of Sn. And it's defined by saying that 2 permutations are equivalent if their corresponding decreasing binary plane trees have the same shape, which is just saying that they're pretty much the same tree up to relabeling the vertices. But the underlying shapes of the trees have to be the same. Okay. And a fun fact about the Sylvester congruence, I used to capitalize Sylvester because I thought it was named after the eccentric 19th century mathematician James Joseph Sylvester. I found out that is not the case. It's actually named after the French word sylvestre, which means forest, because it's coming from trees. So I thought that was interesting. So I no longer capitalize it. And this is a picture of the Sylvester congruence on the left weak order of S4. Okay, so now I can finally tell you about this Coxiter stack sorting stuff. I'm going to let this equiv symbol here, this is going to be an essential semi-lattice congruence on the left weak order of some Coxeter group W. And a basic fact which follows from just the definitions that I've given is that if you take any element of your Coxeter group, it is going to lie in some congruence class, just obviously. And then the fact is that this congruence class will have a unique minimal element, which I'll denote by this pi down equiv of W. So think of this as the downward projection of W onto the minimal element of its congruence class. for example, if I took the Sylvester congruence here and I looked at the permutation 2, 4, 3, 1, the downward projection of 2, 4, 3, 1 in this case would be 1, 4, 3, 2. It's the minimal element of the same congruence class. And then the downward projection of 1, 4, 3, 2 would be 1, 4, 3, 2. And so now my definition is the Coxeter stack sorting operator, S sub equiv. This is from W to W. It's this map defined by saying S sub equiv of W is W times the downward projection of W inverse. And the multiplication and the inverse here are obviously taking place in the Coxeter group. And so this is my definition. Notice that this depends on the choice not only of the Coxeter group, but also of the essential semi-lattice congruence. So there's sort of a lot of freedom in the choice here when you're picking one of these things. Let me just remark very quickly that this Coxeter stack sorting operator will always move you down in the right weak order. This isn't hard to show. And so this is actually a strict inequality here if W is not the identity. So what this means is that if you start at some element and you keep applying the Coxeter stack sorting operator, you're going to keep moving down in the right weak order until eventually you get to the bottom, which is the identity element, and then that will just be fixed. So the diagram of this Coxeter stack sorting operator will look like a tree because everything maps to the identity, which is then fixed. Now you might wonder, why on earth would I call this a Coxeter stack sorting operator? This doesn't look like it has anything to do with pushing numbers in and out of a stack like I did at the beginning of the talk. And the reason is because, first of all, if you take your essential semi-lattice congruence to be the Sylvester congruence, you actually end up getting the stack sorting map. And also, if you take it to be the descent congruence, you end up getting this pop stack sorting map. So because these two versions of stack sorting, which are kind of the most well-studied versions of stack sorting, since there are special cases of this construction, I think it's kind of reasonable to think of this as some kind of very vast generalization of stack sorting for Coxeter groups. But again, there's sort of a lot of freedom in the choice here. So when you want to prove like nice concrete results, I think really you have to make some kind of specific choice about like a nice family of congruences, for example. And I'm not going to tell you why this is true. I think because, well, just because of time constraints, but also because, I don't know, I think it's nice to have a little bit of mystery in a talk, but I could tell you about it if you're really interested later. But for now, I'm just basically using this to motivate the name of this, this definition here. Okay. So let me make a couple remarks about this. I have a preprint that I released about a month ago called Stack Sorting for Coxeter Groups. And in that paper, I focus specifically on a couple types of these Coxeter stack sorting operators that I think are very closely related to the classical stack sorting map. One of them is living in type B. So these are the hyperoctahedral groups. One of them is living in type A tilde. These are the affine symmetric groups. And they're basically these maps that I think are they share a lot of interesting properties that the stack sorting map also has, especially the type A tilde version. These are very closely related to the stack sorting map. But I still think there's a lot to do here, especially just because, I mean, you can choose any choice of an essential semi-lattice congruence. I mean, even in just symmetric groups, even if you're only looking at permutations in symmetric groups, there's still a lot to do because there are lots of choices for these congruences. So I think, if you just pick one of these nice families of congruences and you make the diagrams for these maps, then you might end up getting some interesting structure. And I think there's a lot that could be proven here. So I'd be happy if other people would pick this up and sort of run with it. I will mention that there are these very nice lattice congruences on symmetric groups, which are called the Permutary Congruences. These are actually generalizations of the Sylvester congruence and also the descent congruence. And they also generalize what are called Cambrian congruences. So if you've seen Cambrian congruences before, these also encapsulate those. And the Permutary congruences are nice because they have a nice combinatorial description in terms of these trees called permutrees. And this is basically like what I did with the decreasing binary plane trees for the Sylvester congruence, but it's sort of a generalization of this. And it's nice because you can describe these Coxeter stack sorting operators as post-order traversals on these permutrees. Basically, you sort of traverse through your permutree in a certain order, and you read off the labels in that order. And so it's nice because it's very easy to visualize what this operator is actually doing in these cases. If you look at just the original definition here, you might think like, okay, what is going on here? I have this weird, inverse thing and I'm multiplying. I don't know how to visualize what this is actually doing, but it's really nice for the permutary congruences because you can get a nice combinatorial picture of what it's actually doing. But even for the permutary congruences, I still think there could be a lot to explore because I haven't really looked too deep into them. So I do want to say a couple theorems from this paper because most of what I've been doing so far is just defining things. So I will tell you a couple theorems.
Can I interrupt for a second? There is a little bit of discussion in the chat.
Yeah.
So Dari asks, does Plactic work? And Vic says that he thinks it's not a semi-lattice congruence, but
I think it is not a semi-lattice congruence. If I think that's right. Yeah.
Oh, and
Yeah,
then Stefan, do you want to ask your question? Or?
Yeah, okay. I was wondering because there was a recent preprint by Alexanderson, some co-author, and this study is something they call run sorting.
Oh, I haven't seen that.
And does it also fit into your setting? Okay, if you have not seen that.
Yeah, I haven't seen it, but I will look for it after this, and yeah, I'll be interested to look at it. But thanks.
Great.
All right. Yeah, thank you. Okay, so here's just a fact about the stack sorting map. If you take a permutation, just an arbitrary permutation in Sn, then the maximum number of descents, so maybe I should mention in the symmetric groups, right descents are really the same as what people usually call the descents of a permutation. They're the places where the permutation goes down when you read it from left to right. And the maximum number of descents that a permutation of size n can have is n-1. That's just if it's just the decreasing permutation. But this fact says that if you apply the stack sorting map to a permutation of size n, then that permutation that you get out can only have at most n-1/2 descents. This kind of makes sense if you think of the number of right descents as like a measure of how far the permutation is from being the identity. If you have a lot of right descents, you're kind of far from the identity. If you have very few right descents, then you're close to the identity. So, this sort of makes sense if we're thinking of the stack sorting map as sending the permutations closer to the identity. It's sort of having the maximum number of descents that a permutation can have. You might ask, does something similar happen for these Coxeter stack sorting operators? And the fact is it doesn't. So it's possible to find an essential semi-lattice congruence on Sn and a permutation such that when you apply the corresponding Coxeter stack sorting operator to it, you get something with n-2 right descents, which is like just one less than the maximum number of descents that a permutation in Sn can have. So it's really not doing this halving phenomenon that the stack sorting map did. But what I think is kind of interesting is that you can get something if you restrict your attention to lattice congruences. So here, remember, a lattice congruence has to respect both the meet and the join operations. And for some reason, when you restrict to lattice congruences instead of semi-lattice congruences, then the maximum number of right descents that a permutation in the image can have is 2 times n-1/3, the floor of this. And this is also tight. This is actually attained by the descent congruence, which is the pop stack sorting map. I think it's kind of interesting that there's this sort of 2/3ing result for the lattice congruences. And I think it would be interesting to extend this to other types, because really I was just focusing on symmetric groups. But if you're the kind of person who likes taking things for symmetric groups and extending them to type B or type D or arbitrary finite irreducible Coxeter groups, then I think this could extend in a nice way. I didn't really look into it, so I think this could be interesting. Okay. So just as a recap, we have some irreducible Coxeter group W. H is going to be the Coxeter number. Remember, this is some number that's sort of intrinsic to the group. And my convention is that H is infinity if W is an infinite group. I'm going to define the Coxeter pop stack sorting operator from W to W, which I'm using the same symbol here that I did for the pop stack sorting map, but hopefully that's not confusing. This is just going to be the Coxeter stack sorting operator associated to the descent congruence on W. So what I'm saying here is, remember, if you take the Coxeter stack sorting operator associated to the descent congruence on a symmetric group, that is the pop stack sorting map that Peter Unger and other people have studied in the past. And since we have a descent congruence on an arbitrary Coxeter group, it kind of makes sense to say, well, let's use it to define a pop stack sorting operator for an arbitrary Coxeter group. And my main result about these Coxeter pop stack sorting operators is that the maximum possible size of a forward orbit of an element of W under this Coxeter pop stack sorting operator is exactly the Coxeter number of the group, which I think is kind of nice. And this actually is just Unger's theorem in the case of symmetric groups. Remember, Unger proved that if W is the symmetric group Sn, then the maximum size of a forward orbit of a permutation of size n under the pop stack sorting map was just n. And n is actually the Coxeter number of Sn. So this is like a Coxeter generalization of Unger's theorem. And the proof, I think, is kind of nice. It sort of relies on, well, first of all, it's mostly type uniform in the following sense. First, I handle the infinite groups. The infinite groups are not terribly difficult. You kind of just handle those separately. And then I focus, okay, I say, now I want to look at the finite irreducible Coxeter groups. And there are two cases to consider. One is when the Coxeter number h is even, and one is when the Coxeter number h is odd. And I can handle the case when h is even in a uniform way, just a complete uniform proof for when h is even. And then the other case is when h is odd. But there are actually only two situations when you have a finite irreducible Coxeter group with an odd Coxeter number. One is when you have a symmetric group Sn when n is odd. But I already know that the theorem works there because it's Unger's theorem. So I actually don't deal with that. I kind of just say, well, Unger already proved this, so let's not worry about it. And then the other case where you can have an odd Coxeter number is when you have a dihedral group of order 2m, when m is odd. But dihedral groups are kind of trivial. You can kind of just handle them very easily, and then I don't have to worry about them. So then I get rid of those two cases, and I say, okay, now the rest of them have even Coxeter numbers, and I can give a uniform proof. And I also think the proof is kind of interesting. It also involves the strong Bruja order and how the strong Bruja order is interacting with this pop stack sorting operator and the weak Bruja orders. And there's this sort of monotonicity result involving like longest elements of parabolic quotients. So I think it's sort of a nice proof. But anyway, that's the result here. Okay. So this is a picture of the diagram of this Coxeter pop stack sorting operator on H3. So H3 is one of the exceptional type Coxeter groups. It has 120 elements, which are represented by these vertices. All the arrows here are directed upward, so everything is mapping up to the identity element, which is at the top, and that's fixed by this map. And you can see the maximum size of a forward orbit here is 10. For example, if I look down at this element here, its forward orbit has size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 10 is the Coxeter number of H3. So this is confirming this, this theorem that I had on the previous slide for H3. And this is sort of just an aside. So Nathan Williams contacted me after I put this preprint up, and he told me that actually this pop stack sorting operator is very closely related to something called Brieskorn normal form, which I hadn't heard of before. But this is some kind of normal form that you can define on Coxeter groups, or actually more generally Artin groups. And it turns out that the maximum number of, the number of iterations of this pop that you need to send an element of your Coxeter group to the identity is actually the same as the number of what are called fundamental elements appearing in the Brieskorn normal form of the inverse of W. So I'm not going to say too much about this, but I thought it was kind of interesting. There's this sort of algebraic connection with this Brieskorn normal form thing. And so this theorem that I had a couple slides ago is actually telling you something quantitative about how many fundamental elements can appear in a Brieskorn normal form for your Coxeter group. Okay. Now I'm going to say a map F from my Coxeter group to itself is compulsive if f of W is always less than or equal to pop of W in the right weak order. And the reason that I'm making this definition, the reason it's kind of natural to define something like this is because in the case of symmetric groups, this has a natural interpretation. What this means for a symmetric group is that this map does not remove non-inversions, and it also removes all consecutive inversions. What I mean by does not remove non-inversions is if you have two numbers in your permutation that are in the correct order, meaning that the smaller one appears before the bigger one, then after you apply this map, those numbers will still appear in the correct order in the resulting permutation. They might have moved to different positions, but they will still be in the correct order. And then what it means to remove all consecutive inversions is just that if you have two numbers that are in the wrong order, but they're right next to each other, so the bigger one is right before the smaller one, then those numbers will appear in the correct order after you apply this map to the permutation. So these two conditions together are actually equivalent to saying that your map is compulsive. And the reason I use the word compulsive is because Google gives these two definitions for the word compulsive. One is resulting from or relating to an irresistible urge, especially one that is against one's conscious wishes. And I'm thinking of like a sorting operator that is kind of going through and compulsively removing all of these all of these consecutive inversions. It's sort of compulsively sorting the permutation by removing all the consecutive inversions. But then the second definition is irresistibly interesting or exciting, compelling. And I'm hoping that some people will find compulsive maps to be irresistibly interesting or exciting or compelling. So that's why I use this word. Okay. So here's my main theorem about compulsive maps. If F is a compulsive map on our Coxeter group W, then in fact, the maximum size of a forward orbit of an element of W under this compulsive map is at most the Coxeter number of the group. Okay, so again, I think this is kind of a nice theorem, and the proof also uses this sort of relationship with the strong Bruja order and the longest elements of maximal parabolic quotients, and I think it's kind of interesting. You might think that this would just follow from some of the things that I've said before. So let me recap some of the things that I've said before. Oh, oops. Let me go back. Okay, first of all, I said that the maximum size of a forward orbit under the pop stack sorting operator is H, the Coxeter number. And then the definition of a compulsive map was just, it's a map that moves you down at least as far in the right weak order as the pop stack sorting operator does. Now remember, the pop stack sorting operator is a special case of a Coxeter stack sorting operator. And the Coxeter stack sorting operators always move you down in the right weak order. So what you might think is, okay, imagine I start at some element of my Coxeter group, and I'm going to iteratively apply F and the pop stack sorting operator together in parallel. So they're sort of racing down to the bottom of the right weak order. At each step, you're applying this map. And you might think, well, this condition is just saying that F is going to stay ahead of pop in the race. It's always going to be ahead of pop in the race. So it's going to get down to the bottom at least as fast as pop will. So obviously the maximum number of iterations that you need for F should be at most the maximum number of iterations you need for pop. So this should just follow from what I said before. But this is not actually a valid argument because it is not the case that your compulsive map F will always stay ahead of pop in the race. What it means to be compulsive is that in the first step of the race, F will move ahead of pop, or maybe they'll be tied in the race. So they'll either be tied or F will be ahead of pop. But it's possible that pop will actually overtake F later on in the race, and it can actually end up winning the race. So for example, the stack sorting map, this is West's stack sorting map here. This is actually a compulsive map. That's not hard to show. And if I'm looking at permutations of size 5, I can compute the stack sorting map cubed on this permutation 4, 2, 3, 5, 1. I get something that is not the identity, but pop cubed applied to this permutation is the identity. So actually, in this case, pop wins the race. It gets down in 3 steps, whereas the stack sorting map requires 4 steps. So again, this theorem actually requires its own proof, and it's not just following from things that I've said before. And just a remark is that every Coxeter stack sorting operator, so for any choice of an essential semi-lattice congruence on the left weak order of a Coxeter group, you get some Coxeter stack sorting operator. These will all be compulsive maps. So this actually gives an upper bound on the maximum size of a forward orbit of one of these maps. But this is not always going to be tight. So if you're interested in some specific Coxeter stack sorting operator coming from a specific essential semi-lattice congruence, this might not be equal to H here. And so it might still be an interesting question to determine what this actually is. Maybe it's like H over 2 or something. It could be smaller. This is just an upper bound. Okay. So that was sort of the Coxeter stuff that I wanted to talk about. So are there any questions up to now about like the Coxeter stuff that I've talked about? So I'm about to shift gears and talk about meet semi-lattices. Okay. So I'm going to let M be a meet semi-lattice. Okay, I'm actually saying it's a complete meet semi-lattice, but just, okay, it's a meet semi-lattice. And I'm going to define this map pop sub M. This is the meet semi-lattice pop stack sorting operator on M. And it's defined by saying that pop sub M of X should just be the meet of basically the things that are covered by X. So this big wedge symbol is the meet of all of these things. This is the set of things that are covered by X in the meet semi-lattice. And then I also threw in X here. The only reason for throwing in X is to make sure that this is doing what I want it to do on the minimal element. But in general, you should just think if you take a non-minimal element, then really I'm just taking the meet of the things that are covered by that element. That's all I'm doing. And the reason for defining it this way is that if M is the right weak order on a Coxeter group, then actually this meet semi-lattice pop stack sorting operator is the same as this Coxeter pop stack sorting operator that I defined before. This is not hard to show. This follows from some basic Coxeter theory, but this is sort of motivating defining this. So for example, if M is just the right weak order on a symmetric group, this definition here recovers the original pop stack sorting map that Peter Unger and other people have studied. Okay. Again, we can define compulsive maps in this setting. We'll just say that a map from M to M is compulsive if f of x is less than or equal to pop sub M of x for every x in our meet semi-lattice. Now, if M is the right weak order on a Coxeter group, so that this is actually just the Coxeter pop stack sorting operator I was discussing before, then we have this inequality here. And this is because, well, so what is this saying? This is saying the maximum size of a forward orbit under the compulsive map is at most the maximum size of a forward orbit under the pop stack sorting operator. And the reason for this is I just gave you two theorems. One was that this thing here on the right is equal to the Coxeter number h. And the other theorem said that this thing here on the left is less than or equal to h. And so when you put those together, this thing on the left is less than or equal to this thing on the right. But this is not true for arbitrary meet semi-lattices. And this is an example of where it fails. So I'm not going to go through this, but if you stare at this, you can check that. So the green arrows here are a compulsive map. So for example, this map sends the top element down to this element over here, which then goes here and then goes down to the bottom. And so these green arrows are defining actually a compulsive map. That's not hard to check. And the maximum size of a forward orbit under this green map is 4, whereas the maximum size of a forward orbit under pop on this lattice is 3, and 4 is not less than or equal to 3. So this inequality does not always hold. And I think it would be interesting to understand, like, what are the finite lattices where this actually holds? I haven't really thought about this, so I don't know how hard it is. It could be very hard, maybe not, I don't know. But this is just asking, what are the finite lattices? So I'm only focusing on finite lattices in this question, just for simplicity. What are the finite lattices such that this inequality holds for every compulsive map F? And even if this is like really hard to prove, I still think it would be interesting to have a sufficient or necessary condition for when this holds. So for example, I think it would be interesting to have a sufficient condition where you say, if my finite lattice satisfies such and such property, then this inequality will hold for every compulsive map F. And then you say, oh, well, by the way, right weak orders of Coxeter groups satisfy such and such property. And that explains in a lattice theoretic way why this inequality is holding for right weak orders of Coxeter groups. Because basically, I know that this is true because I have these two separate theorems which were proved in a sort of Coxeter theoretic way using things like the strong Bruhat order, and I put them together and I get this inequality. But I don't really understand from like a lattice theoretic point of view why this is working. So I think it would be interesting to have just an understanding of why this works for, like, what is special about the right weak order of a Coxeter group from a lattice theoretic point of view that makes this actually work, which doesn't work, for example, in this lattice. Okay. Now, finally, I want to tell you about pop trivial lattices. Oh, wait, sorry. Okay, that's the next slide. Let me just make a couple remarks. I have this preprint, a different preprint that I released about a month ago called Meeting Covered Elements in Utamari Lattices. And in this paper, I study these new Utamari lattices, which are sort of generalizations of the Utamari lattices, if you're familiar with those. They have a lot of interesting structure. And basically, I just studied these pop stack sorting operators on those. But I think there's still a lot of interesting stuff that you could do here because there are tons of interesting families of lattices. And so if you just pick one, or it could be semi-lattices, it doesn't have to be a lattice. Again, you could just sort of plot these, diagrams of the operators, and you might get some interesting structure. And I think probably there are some interesting examples of lattices where maybe there's some interesting structure showing up. But obviously, I haven't gone through like all of the interesting examples of lattices because there are lots of interesting examples of lattices. And I do have this one conjecture about Utamari lattices. So here I'm letting tam sub n be the nth Utamari lattice. If you're not familiar with these, just think of these as some very nice lattices. They can be defined on dict paths, for example. And they have a lot of interesting connections with algebraic combinatorics. 0 hat here is going to be the minimal element of this lattice. And I'm going to let a sub t of n be the number of elements of this Utamari lattice that get sent to the bottom element after at most t iterations of this pop. Okay, so this is just saying that it's the number of elements such that they get sent to the bottom after t or possibly fewer than t iterations of this pop operator. So I count those up, that's a sub t of n. And then my conjecture is that when you take this generating function here, you get a rational function. So just a polynomial in x divided by a polynomial in x. I know that this is true when t is 1, because when t is 1, you just get powers of 2 here, and powers of 2 have a rational generating function. And I also know that it's true when t is 2, because in that case, you get what are called the Pell numbers. They also have a rational generating function. But the conjecture is that for every fixed t, this should work. This should give a rational generating function. Okay, so now I'll tell you about the pop trivial lattices. Or actually meet semi-lattices. I'll say a meet semi-lattice is pop trivial if it's basically trivial in the sense that every element gets sent immediately down to the bottom by this pop operator. Okay, so it's sort of the most uninteresting dynamics that you can imagine because it's just saying after one iteration, everything gets sent down to the bottom element and then it just stays there. So there's nothing interesting happening from a dynamical point of view. But there could be something interesting maybe from a lattice theoretic point of view. And so my question is, can you characterize the finite pop trivial lattices? I mean, you could also phrase this for like meet semi-lattices or infinite things, but I'm just going to focus on the finite pop trivial lattices. And I do have some partial results here. One just says that every geometric lattice is pop trivial, and the other says every pop trivial lattice is atomic. These inclusions are not equalities, though. So let me just say what these words mean. When you have a finite lattice, it will have a unique minimal element. And the things that cover that minimal element are called the atoms of the lattice. And a lattice is called atomic if every element in the lattice can be written as a join of some set of atoms. So atomic just means every element is a join of atoms. And then geometric can be defined in a couple different ways. One is to say that these are the atomic semi-modular lattices. Or alternatively, if you like matroid theory, then these are just the lattices of flats of finite matroids. So you can think of this as just saying that the lattice of flats of a finite matroid is always pop trivial. Okay. Okay, so at the beginning of this talk, I made some references to the Lorax by Dr. Seuss. And so I want to make a couple other stronger connections between my talk and the Lorax. So in the Lorax, if you remember, actually, I have it here. I'm in a library and I'm in the children's librarian's office because the Wi-Fi is better here. My mom's the children's librarian. So she got me a copy of the Lorax. But in this book, this kid goes to like this tower and there's this guy named the Onceler and he's living up in the tower. And the kid like basically sends some money up in this pail. And then he's like wanting the Onceler to tell him some story or something. And so then the Onceler tells him this story about the Lorax, which is basically a story about how this Onceler guy like single-handedly destroyed the whole environment. And then at the end of this story, the Onceler's like, okay, kid, I'm going to give you the last truffula tree seed, and it's now your job to go plant this seed. And he says, not only plant this one seed, but you have to grow a forest and protect it from axes that hack. And I always thought this was kind of weird because like, okay, he's the one who destroyed the environment and he's the one who had the seed. Like, why didn't he go plant it? But anyway, I think I'm kind of like the onceler here in the sense that, you probably just came here wanting to hear a story and, wanted to hear some math. And I want to give you a seed, which depending on your taste could either be this definition of a Coxeter stack sorting operator or the definition of the meets semi-lattice pop stack sorting operator. And my hope is that someone will go plant this seed and grow a forest, literally in the sense that you can take say a family of meets semi-lattices and plot these diagrams, and you'll actually get a family of trees, which is a forest in the graph theoretic sense of the word. I don't know what this other sentence would mean graph theoretically, but okay, so you can do this. And my hope is that someone will explore this further, because I think there's a lot of interesting things that are left to be uncovered here. Okay, so that's all that I wanted to say. So thank you very much for coming. Also, I'll explain this in the Lorax at the end. The Lorax writes this word unless on a pile of stones in this shape here. And then the onceler interprets this as, unless someone like you cares a whole awful lot, nothing is going to get better. It's not. And this was definitely meant to be like about the environment or something, but you could also interpret it in terms of like non-invertible combinatorial dynamics or something like that. So anyway, that's my talk.
All right, let's thank Colin. Does anyone have any questions?
I have one question. First of all, thank you for the nice talk. I remember that at the GSCC you proposed an open problem where you studied the average number used for pop stack sorting. How does this conjecture on this average number generalize to your setting here?
Yeah, so I made the same conjecture basically in type B and type D. And the reason for that is because the type D is a little messy, but like overall on average, what the pop stack sorting map is doing to a permutation is kind of the same as what it's doing in type D, except for some weird stuff that happens like near the origin. And so I basically made the same conjectures for those types as well, but they are also open as the type A case is also open. So maybe for other people, I'll just say the conjecture says that if you take so the maximum number of iterations that you need to send a permutation to the identity under the pop stack sorting map is n-1. This is Unger's theorem. But my conjecture is that asymptotically, the average number should also be roughly n. So basically, the worst case scenario is sort of also the average case.
Thank you.
I also have one, and well, first of all, thank you for the talk as well, Colin. So in your stack sorting for Coxeter groups, I'm not sure if it will be in all cases, but does in any case this sorting, when you change from congruence class to another congruence class, does the minimal element also get mapped to a minimal element, or somewhere in between it gets skipped to somewhere in between?
Wait, so are you considering multiple congruences here?
No, you just have one congruence, you take minimal element and, well, you take an orbit. When you get to a minimal element, does it keeps staying on minimal elements?
So the minimal elements are actually exactly the elements that get sent right to the bottom. So this is because being a minimal element is the same as saying that you're that you are your own downward projection. So then you just get like W times W inverse.
Okay, perfect. Thanks.
I actually need to go. So before we get to more questions, let's thank Colin again, and then you can hang out longer if you'd like to. So thank you very much. Great talk.
Thanks.